So this video is about the recovery of the geometric fundamental group from the arithmetic fundamental group. And so by recovery I mean an interpretation or some sort of absolute Anabelian reconstruction. And so so let's recall that if we're given a curve or a variety more generally over a field K, that we have this augmentation map. Or sorry, this spectral sequence. So this is the augmentation map here. So this is sometimes called the augmentation. Okay, so this is a relative thing. So relative is in you're working in the category of schemes over a field or groups over another group, versus just working absolutely, meaning just with the single fundamental group. So that's what absolute Anabelian geometry means. It means that we're going to be working with this single fundamental group here. And so the theorems that I want to talk about is the following. So it says that if K is a number field, or p-adic field, which by p-adic field I mean a finite extension of QP, then well, you'll see what they are, but I'm just going to write it like this: pi of x. Then let's like this. Then the sequence star can be constructed from pi of x alone. Okay, let me mention something else about this, is that here, in order to define pi of x, we need a geometric point. So a point in k bar. So k bar is the algebraic closure for this video. And here, this induces a point of, if I were going to base change, so this is the fundamental group. Okay, so we still have a point x bar in this one. And the induced map here, so the map when you chain the map from spec k bar to x to spec k, is actually what's going to give the embedding and induces this. So this is induced from, so this sequence here is induced from maps of pointed schemes. Okay. So when I write that down, I've actually chosen a base point, and then these are genuine morphisms of schemes. Okay, so now I'm going to go about reconstructing these things, and there's kind of two cases. There's the number field case, there's the p-adic field case, and I'm going to do two different things for this. The origins of this theorem, or what I'm going to talk about, are in the beginning, the section 1 of absolute Anabelian geometry of hyperbolic curves, and this is in absolute Anabelian geometry 1. Section 2. Okay, so let's do the number field case. And let's start with a lemma. So this is from Fried and Jarson, Theorem 5.10. Okay, so let F be a number field. Okay, so every topologically finitely generated subgroup of GF which is normal and closed, is trivial. Okay. All right, and so now let me give you another lemma. So if x is a curve over a field K, then this geometric fundamental group is isomorphic to this guy. Okay. So I mean, this comes from the comparison of these analytic fundamental groups, or the topological fundamental groups, with the Étale fundamental groups. So this is here we're going to have a bunch of generators, AI, BI, CJ. So these range from 1 to G. These range over the number of punctures. So this is a okay. So this is a punctured curve. Okay. And, okay, I guess maybe I should have said connected or something, but I think you understand the point. This is going to be a curve of type GR. And they satisfy this relation like this. Cj, this goes up to R, this goes up to G. Okay. All right, so this is a finitely generated group. Okay, and so now we can give this lemma. So this is the recovery lemma, and this is due to Tamagawa according to Machizuki. But this is in, I think, absolute Anabelian geometry of hyperbolic curves. This is Machizuki. But he says that it's due to Tamagawa. Okay, so let's let X over F be a variety over a number field. Okay? Such that and suppose this thing here, delta x, is finitely generated, is topologically okay, so like in the curves case, so like in the exact case for curves. So then delta of x, let's say the unique, let's do it like this. Let me go back. So I don't know how to say this, but let me say this. Delta of x is equal to the unique maximal closed subgroup of pi of x, which is topologically finitely generated. Or you can say that this thing here is the intersection of, let's call these deltas, where delta naught here is a closed subgroup in pi of x, where its delta naught is topologically finitely generated, and that's it. Okay, so this is another way of doing it. So you take all the closed subgroups, which are topologically finitely generated. Then you intersect all of them, and you get this guy. All right, let's give the proof. So from the exact sequence, so proof. So from the exact sequence, it goes like this: 1 to delta of x to pi of x to gk. Here, it's clear that we get that you know, delta of x is contained. Well, this is the definition. It's the kernel of this map. Okay? Okay, so let delta naught be a maximal closed topologically finitely generated subgroup of pi of x. Okay, so by the lemma, we clearly have this map, delta 0 subset of the kernel of p of x. Okay, so we're going to, so this is, you know, we have a finitely generated, so let's go back to the lemma here. So we have a topologically finitely generated subgroup, okay? And then the image is going to be closed and normal. So why is the image? So I guess we need to check, so this is missing, is that we need to check the image is closed and normal. Okay, so, but since it's maximal, okay, since it's maximal, this implies delta 0 is equal to delta of x. Okay, so I guess this is the tricky part, is that you need to check that the image of these things are always closed and normal. All right, so let's do the local case. The local case is substantially more involved. So we need a lemma. So let K over QP be a finite extension. Let G be the absolute Galois group of K. And then let L be a prime number. Okay? And what I want to show is that the dimension, QL dimension, of the Abelianization after a tensor up to QL, so this detects the degree of the field extension. If L is equal to P, and 1 if L is not equal to P. Okay, so in particular, doing this and looking at the dimension allows you to detect what this is. And so another thing to point out is it's important here that we tensor with Z hat. If we tensor with Z, we get something else that's weirder, right? So that's kind of important. Okay, so let me give a proof Maybe I need some. Maybe I need a. Before proving this one, I guess I need a lemma. Oh, okay. I'll prove this lemma afterwards. I'll show you where it comes up. Okay. So. All right. So here's my lemma here. Okay. So here's the proof. So by local class field theory, we have this isomorphism, this Artin map between the abelianization of the fundamental group, and the units completed of the field. Okay, and so the completion is with respect to taking nth powers of elements. Okay, so we're now we can use the description of K. So we can now use a description, which I'll do on the next page, of K cross. Okay. So we know that K cross is really, so the units are really the units times some power of a uniformizer. Okay, so every element in K we can pull out some appropriate power here and then multiply it by times a unit. And so I guess pi here is some uniformizer. Okay, so this is a choice here. Okay, now we can study what this thing is. So this thing, the units of the ring of integers, so this is really the tight cumular elements and another group of units here. So we have this product here as well. Okay, so M, so this is the maximal ideal. And then mu k, which is the same thing. These are all the roots of 1. And this is the same thing as the tight cumular lift of, so this is the residue field. This is isomorphic to little k cross. This thing is this, I guess, get rid of that. This is the residue field. Okay, so we have this description as well. Okay, and then we can even go further, where 1 plus m, there's a p-adic analytic map, or a rigid analytic map, which is the logarithm into pi ok. Okay, so by the way, this okay, so let me say a little bit about this. So the logarithm here of 1 plus x is defined as usual. So this is the p-adic logarithm. So it looks like the log base e. And it converges when the absolute value of x with respect to the valuation is less than 1. Okay, so this is when this series is defined, and then you can extend it using multiplicativity. Okay, so if you want to define it elsewhere. Also, by the way, there's this inverse map. Is an inverse, and this is defined for I guess when absolute value of x is less than the absolute value of p to the 1 over p minus 1. Okay, so we have this. I should also note another thing. Is that the last thing I need to note is that that m is just pi times ok, which is so this is okay, so this is isomorphic to, well, it's actually equal to, let's do it like this, it's pi times omega 1 of ZP plus omega d of ZP, where these guys, this is a basis for OK as a ZP module. And what else do I need to say? I think that's all I need to say. Oh, D. What's D? D is K to this degree here. Okay. So putting these things together, what do we get? We get that that OK cross is the roots of unity, and then we have this exponential pi, and then we have omega 1 ZP plus omega d ZP, like so. Okay, so this is what we have, and so this is just isomorphic to, you know, some torsion group with something isomorphic to as a group ZP to the D. Okay, and D is again this D. All right, so okay, so another observation, let's also observe that this guy here is really this, since torsion is torsion and ZP hat is ZP. So when we do this pro-finite completions of those guys, we get the same thing. Okay, so the rest follows. Okay, so we have this, and so what was the statement? The statement was about this group here, which is really this dude here, and we want this dimension. And this dimension here pops up exactly from this presentation of the units, which appears in K cross. Okay, so it's this uniformizer part, and then we have this. So okay, so again, all right. So the rest follows from the fact that, okay, what am I saying? The theorem now follows from the fact that ZP tensor Z hat Q to the L, well, this is going to be Q to the L when L is P only, and 0 else. Okay, so again, we have this thing, right? So this is really isomorphic to some Z hat cross this OK cross here, and so this is, you know, Z hat cross torsion cross this ZP to the D. All right, and then this part. Okay, so now we can see that here's the +1, and then here's the degree part. All right. Okay, so the lemma that I wanted to show was I'll just do it really quick, is that ZP tensor hat of ZQ is 0 for P not equal to Q. And this is kind of confusing. The proof is easy. So this is okay. So every element is arbitrarily small. Every element is arbitrarily small, but the only arbitrarily small element is 0. Okay, so note that this thing is essential. Okay, so this thing ZP tensor. So these are primes. P and Q are primes, by the way. Okay, this dude is over Z is funky. Okay, and non-zero. Okay, if we so this is the subtle difference between tensoring over Z hat. So that's what I mean by this thing. This is tensoring over Z hat, and this is tensoring over Z. So here, okay, so we have an injection. So here's like kind of a proof of its non-zero-ness. So Z injects into ZL. Okay, and so ZP over Z. So this functor here is exact since ZP is flat. Okay, so then this implies that this guy here is an injection. So ZP tensor Z over Z. These cancel. So now we just kind of slap this functor onto this map. And now we have ZP tensor Z over ZL. And now we have a copy of ZP inside, right? Similarly, there's a copy of ZL inside here. And also, you'll be able to show that multiplication by P and multiplication by Q are both injective. Actually, multiplication, or it's actually bijective. Because this will preserve injections and surjections. So, yeah. So then this shows that this thing is actually it actually will turn out to be a Q algebra. So this thing's kind of this crazy thing with lots of stuff inside of it. So you really need to do Z hat. Okay. Again, the more important point, I guess, about all this is that here this allows you to detect, just from given this group G, right? You can detect the residue characteristic from this thing. So it's like you can look at all these, and you look at the prime where this thing is not equal to 1. And you can test for that, and that's how you can spit out, just given an abstract profinite group. Suppose you know that it's the Galois group, the absolute Galois group of a local field. You can determine its characteristic just from knowing what doing this trick. Okay. So finding when it's bigger than 1. Okay, so again, the upshot. So given a profinite group, G isomorphic to, say, GK, one can detect the residue characteristic. Okay, so let's make a definition. So the definition is as follows. So let G be a group, be a profinite group. Okay, and what I'm going to define is I'm going to define the dimension, the QL dimension of G. Okay, and this is going to be defined to be equal to the dimension QL of, we take the abelianization, we do the profinite tensor with QL. Okay, so now we have this thing that we defined. Okay, so we have this number. Okay, and maybe I'll call this dim L as well, to shorten it even more. Okay? Okay, so here's a lemma. So given an exact sequence of groups, So let's say profinite groups. So let's just do this completely abstractly. I have nothing in mind. Okay, so we check. Oh, sorry. Dang it. Well, okay. This is okay. We have that the dimension is plus. Okay, so that this thing is additive in exact sequences. Okay, so let's prove this. The proof. Okay, so you really just need to check that. You check that abelianizations preserve exact sequence. Preserve exact sequences. And then you just have like use the dimension formula. Okay, so what do I mean by that? So let's take an exact sequence here. So this is still surjective after we take abelianization. All right, that's clear. This is surjective. So then this is surjective onto the abelianization, and then this, the abelianization, any map to an abelian group factors through its abelianization here, and then you can also check that this is still the kernel. Okay. Okay, so now let's do something else. Let me see if I hopefully I didn't skip anything. Okay, that's good. Okay, so let's do another lemma. So let G be isomorphic to the absolute Galois group of a p-adic field. Okay, and what we've just shown is we've shown that that we can recover the residue characteristic from just the absolute Galois group, so that the characteristic of K is P. K is the residue field if and only if P is the unique prime where this dimension, let's say P, is not 1. And moreover, that this dimension is actually the degree plus 1. So one of the questions we can ask is, okay, so we've done this with the absolute Galois group. So one of the questions we can ask, so question 1, is how do we get the characteristic from the fundamental group? Get the characteristic from just the fundamental group of a curve. Another question we can ask is how do we recover? How does this help us get? Does this help us recover the absolute Galois group, or sorry, the geometric fundamental group? Okay, and so the answers are given in some theorems. So theorem, and so we'll call this the recovery of the residue characteristic from, let's say, pi, from the fundamental group. Okay, and so we're going to let K over QP be a field. And then we're going to let X over K be a curve. All right, and the thing that we're going to have is that so the dimension. So if we take 2 primes, we can consider the difference of the dimensions between 2 primes. And this is going to be 0 when L and L prime are distinct, and not equal to P. Okay, and then it's going to be this degree when L prime is P and L is distinct. Okay, and I guess technically I should have some other condition where it's the minus of this. Okay, so all right, so we have this thing, or maybe I could do, yeah, okay, so let's just do it like this. Okay, it's kind of a little ugly, but whatever. So you can notice that this condition, this thing already popped up when we were doing for G abelian, and that's kind of the truth that kind of appears in the proof. Okay, so I want to answer the second question though first. So let's answer the second question, and this is the recovery of the geometric fundamental group. Okay, so I guess I didn't really need period, but oh well. Okay, and so let K over QP be a finite extension. Okay, and we're going to let X over K be a field, or sorry, be a curve. Okay, and this is how we're going to this is how we can recover delta of X. So the geometric fundamental group. So this is the intersection over all Clopin subgroups satisfying the following numerical condition. It's that the dimension of P of pi 0 minus the dimension L of pi 0 divided by its index is equal to D, where D is equal to QP, which we could recover from the previous theorem. All right, so that's a statement, and that's how this is recovered. Okay, so and note that this allows us to recover this because we test and we see which ones are non-zero, and then once it's non-zero, we take its absolute value and we get this number. All right. So let's give a proof of the recovery of the residue characteristic in degree. So the first theorem. So we're going to use our lemmas as expected. So the point is that this guy here is profinite free, as we showed before. Okay, and hence, so these dimensions for all L and L prime. So the function is just a constant function, the function which takes a prime and it assigns it to this dimension. Okay, so All right. So let's kind of let me write out this what this is now. So so dim L of pi. Let's actually do p here. Dim p of pi minus the dimension, the L dimension of pi. Okay. So from additivity in exact sequences, we know that this is the dimension of delta plus the dimension of g minus, now we have the dimension, oh sorry, p's here, I did it again, l's of delta minus plus the dimension L of g. So we're using the fundamental exact sequence. These two things are the same. And so this is just the dimension of p of g minus the dimension L of g. So g is gk. So this thing is equal to kqp. Okay, so this was 1 and then this was 0 from our previous lemma. Yeah, so that's from here, or where we proved it. Here. So this is this thing coming from the unit groups. Okay? So this is that's what we have there. Okay. So so okay, so this shows us, oh yeah, so that proves so that proves what we wanted, okay? So so that's when we took P and okay, so that's when we took P and L. For L and L prime, okay, the dimensions are constant. Because they are so on this guy and G, okay, and hence we're done. That gives us the 0 part here. All right. So to understand the proof of the second theorem, I want to do so an interlude, so something that helps me think about fundamental groups. So and I just think this is instructive, so I'm just going to include it. Okay, so I'm going to write something that's kind of false, but in this exact sequence, so again, the exact sequence, maybe I should always have it up. So this is for local fields, but the statements I make are going to apply more generally. So this guy is the openish subgroup of x. Oh, let's say pi of x corresponding to the cover like this. Okay, so this is false. All right. But this is kind of an idea that can help us start with the proof of this theorem here. But let me just say why this is false first. This guy here, we can't do the Galois correspondence. Okay, so the correspondence again says that if you have a scheme, so the open subgroups, let's say so these guys here are finite atoll covers. Okay. Okay, and not anything more than this. Okay, but there's something useful here. What's useful here is if you just think about this, just even in terms of fields, this is stronger than the usual Galois correspondence. Okay, so okay, that's all I wanted to say about that. And then what else did I want to say? Oh, okay. The other thing that I wanted to say is the clear thing is that this thing is not open. It's closed. Okay, and let me make some more remarks about this. So, okay, so the closedness of delta x. Let me just say some things about this. So, here's a proof. Here's a proof that shows that it's not open. All right. So, if it were open, then what would we have? So then, pi of x minus delta of x. Okay. Let's actually do this. So then, if it were open, so pi of x. Okay, so we could write this as a union of cosets of x. So this is just kind of the coset decomposition. But if these were open, this would be a cover by open sets. So it would admit a finite subcover. So this is some G and some set. Okay. So this would be a finite subcover. Okay, which would imply that pi of x mod delta of x would be finite, which is a contradiction because pi of x mod delta of x is the absolute Galois group of a local field. Okay, so this is kind of a little aside here to show that it's not open. To the actual proof proceeds as follows. So delta of x is equal to the kernel of p from pi of x to gk of x, right? I.e., it's the inverse image of a point of the identity which and this set here is closed. Okay, so that's the idea, but how do you show that? So let's see. Let's do another aside here. So let's see. To see that this singleton is closed, we just observe that the maps here. So if G, okay, so let G be a profinite. So this is for, maybe I should do this for an arbitrary profinite group. So let's take H, a arbitrary profinite group. So H is, say, the limit of these HIs. These guys are continuous, with this being the discrete topology. Okay? In particular, what does it say? Well, so this is given the discrete topology, meaning that all the subsets are open and closed. Okay, so in particular, the kernels of HI are clopin. Okay, so they're the inverse image of both a closed set and an open set, right? And okay, so in the union of anything not in the kernel of a finite quotient is an open, only not containing the identity. So let me repeat that again. So the union of H mod Ki, so let's say, let me write this out in symbols. The union of H without Ki, these are opens, and so these are equal to, I claim that this is equal to H without the identity. So, i.e., every element is eventually contained in a kernel. All right, so that's a little thing about why that's closed. Okay. Okay, so we can approximate. So let's talk about the approximations of this cover. And the obvious thing to do is to base change. So consider so K0 over K, which is a finite field extension. Okay, if we base change the atoll map here, via the map X goes to spec K, the structure map, then we get the following map to X. X is XK. Okay, which is atoll. Okay, so base change by atoll maps are atoll. So this atoll map, okay, so like when we take a large field extension, that's kind of like approximating the algebraic closure. So atoll maps correspond to finite index open subgroups. So let's call pi 0. This is defined to be pi of x k0. This is open in here. So open is in finite index is redundant. Open implies finite index. Okay. Okay. So this is what we have on one hand. Okay. We have this. We just have this open under open subgroup. Okay. And the Kunath formula. What does this tell us? The Kunath formula tells us that pi 1 of x over spec k, spec k0. So this breaks up as pi 1 of x, so that's pi of x, and then pi 1 of spec k cross pi 1 of spec k naught, so this is gk naught, and over gk. Okay, so this is what Kunath formula tells us. Okay, and so what this is really saying, if you're familiar with how tensor products work or fiber products work, is that so this is saying that this guy here, pi naught, so this is pi naught, is the inverse image of gk naught under p. I've been realizing I've been using two p's, but this p here is, so we have this exact sequence. Okay, and p, and then since this is a finite extension of a field, it corresponds to an open subgroup, and then we can take the inverse image here, which will be an open subgroup here. Okay, and okay, if we do this thing, we kind of see that we get this product, and this product is, one way of seeing this product is the inverse image of an open subgroup. Or sorry, the one way of seeing, one way of seeing the inverse image is this fiber product. Okay, so I want to make some statements about this. So what I want to note is that this guy here, G, I'm going to call G GK, and then we'll call this G0. So this is going to be the same as G0, which is going to be the same as the degree of x0 over x. So this is one of the ideas, okay? So, all right, and the idea, I guess, would be, so this is one particular case, and so note that this is true. Okay, and let me just kind of maybe make a remark about this. So, so let me make a claim and then a proof. Okay, so claim. If G0 is D, okay, so again, then this implies that pi P inverse of G0 is D. Okay, again, I'm using this notation where pi is pi of x, G is G of k, okay, and then the subscripts with zeros, pi of x0, x0, did I say what x0 is? This is x0. Okay? And that's what we have. Okay, so let me just say the proof here. So let's take this. So pi of P inverse G0. So this thing is the same thing as, so from the correspondence with the tall maps, this is the degree of x0 over x. And this is the degree of k0 over k. Okay, by base change. So this is base change. And this is from the correspondence. Okay. So here's kind of like a quick thing, so that if so where this intersection comes from. So if in a special case, so if x0 over x is Galois, then the map here G of x0 over x, this is q0. So this is continuous with this being the discrete topology. Okay, so this is continuous. And then this Q inverse of 1, this is K0, or I guess at least this is pi 0 in this particular case. Okay, and as we vary over the various so as we vary over the various pi zeros, okay, what happens? Well, if we take the intersection of the pi zeros, so this is going to be a closed set, and the union of the pi zeros, this is going to be an open set. Okay, so this goes along with what we were talking about with the other thing. So this is what we're after here. So I want to talk about a construction, and this is kind of this arithmetic geometric factorization. Of covers. Okay, so let's take Z to be a scheme over a field K. And let's consider now the I guess maybe I could take it over a field F, so that we're using different letters, and then let's take a cover. Let's call it Z0 to Z. Okay, so this is finite et al. And what I want to do is I'm going to factor this as in the following way. I'm going to factor it as a base change. So this is a base change followed by a geometric, some sort of geometric thing. And this is going to be this arithmetic thing. All right, so what do I mean by geometric and arithmetic? So let me try to describe what's going on now. I'll do it over here. So we have pi of z, okay, and this has its sequence. So this is delta of z, 1. This goes to g of f. This goes to 1. Okay, it has a projection map here. Under the projection map, we can consider, okay, so then we have pi of z0. Okay, and this sits inside here as a subgroup. Okay, and what we can do is we can consider the map here P to G0. So this is G0, this is P of pi of Z0. Okay, this goes to 1. All right, the other thing that we have, the other part of this thing is this arithmetic part. This is delta 0. And this is just the intersection of pi of z0 with delta of z0. Okay? So we have this this exact sequence that's induced by this exact sequence here. All right, that's all good. But what we can do is we can consider now this the inverse image of P here. So this we can now take pi of z of f0, which we saw was the inverse image of g0. So this is this stupid base change one. Okay, so here these are exactly equal, and it turns out that if you take the inverse image of g0 so that we're taking the inverse image of this map here, well, the kernel is still in this inverse image, so this is going to remain the same. So this is delta here. This is still delta z, which was delta. So we call this thing delta. So these are the same here. Okay. So what we've done is we've separated this into two pieces. There's kind of this geometric piece here, and then there's this arithmetic piece over here. So we factored into two pieces. Oh, okay. Sorry. So let's. The arrow's going the wrong way. So these are not arrows, these are inclusions. So this is open, right? And then we have this inclusion here, which is open, right? And it turns out that this is also open. Okay, so we have this factorization. And it turns out that, okay, so these are the two maps here. So the degree of f, let's call this A, and then we'll call this G. So it turns out that the degree of f is equal to the degree of A times the degree of G. Okay? And in this case, we've seen before, so that this guy here, so this means that, maybe we didn't need to do that. Maybe I'll do, I don't want to do the whole thing in blue. So this thing is delta 0, and then we have the arithmetic piece, which is G of F G0 here. And then the full cover is, I don't know, maybe we can do this in red. So that's this full thing here. So this is going to be pi 0. Okay, so this is the magic formula that I wanted to talk about, and this is kind of how, this is the statement that you can break up these covers into a geometric piece and an arithmetic piece. So yeah, so here's the, maybe I should have done that, but this is quite a nice little picture here, and it's a nice way to think about it, is that you can do this base changey thing every time. Okay, and I want to use this idea. All right, so let's prove our claim now. I think we're in a good position to do this. So again, the lemma is the following. It's that, so let x be a curve. Over K, which is a p-adic field. So this is a finite extension of QP. And we want to, and so let pi 0 be a subgroup of, an open subgroup of pi, which is going to be defined to be equal to pi of x. Okay, and the statement is that this dimension of p, so pi 0 minus the dimension of L of pi 0 divided by this degree here. So this is equal to K QP if and only if pi 0 is P inverse of G0 for some G0 subset of G open. Okay, so here what I'm implicitly using some notation. Let me just remind you what it is. So here we're using this sequence again. P G. Okay, so this is GK. Right. Delta of X. This is the geometric fundamental group, like so. Okay. So in this notation, so we want to show that this is true if and only if, so that this characterizes this. Okay. So the proof. Okay, suppose pi 0 is P inverse of G0. This is the easy part. So if this is the case, this implies that pi 0 is pi of x of K0, where K over K0 is a finite extension. Okay, so from this we get an exact sequence, pi 0 to G of K0 to 1 to delta of delta 0, like this, like 1. Okay, so this is again delta of x of K0. That's supposed to be a subscript. And this is pi, well, I already wrote that before. Okay, and from our previous lemma, our recovery of the characteristic of the residue field, we know that, what did we know? We know that the dimension, first of all, we can recover what P is, and then we know that the dimension of pi 0 minus the L dimension of pi 0 is the degree of K0 over QP. From our previous claim, we have that this degree here, well, this is the same as G0. This is G0. Okay, and this was the same thing as K0 over K. Okay, and we put these two things together. So what do we have? We had the dimension of P of pi 0. We had the dimension of L of pi 0 divided by this degree. Okay, this top one was K0 over QP. The bottom one was K0 over K. Okay, and then this thing breaks down. KQP, K0K. These cancel, and then we get a result. Okay, so that goes the forward direction. So conversely, suppose pi 0 is an open subgroup of pi with this satisfying the inequality. Dim pi 0 minus L pi 0. Pi 0 is equal to K over QP. Well, using our factorization, so pi 0 corresponds to some pi of x0. Okay, and we can factor any cover. We can use our factorization of covers. To get the following, to get that this thing pi 0 is delta 0 times G0. And more precisely, this comes from a factorization where we had x0 to x, and then we kind of base change like so. Okay, and this cover is completely geometric. Okay, and so we want to show is that this part here has degree 1. Okay, and so looking at this formula here, so So again, we can write down our sequence. Okay, so now what we can do is we can write down our sequence for pi 0. So we can write down our sequence for pi 0 to give the following. So we know it's over, we know it's field, okay? And we know, so for pi 0 we have this delta of x0, pi of x0, and then, so this is pi 0. Then we have g0, like this. Okay? And then we know that the top piece from our lemma, dim p of pi 0 minus dim l of pi 0, this is equal to k0 over qp. Okay, and again, this factors. So k0 over k, k to qp, and putting this into putting this into the equality, into our assumption, we get the following. Well, we get k0k, kqp over pi 0. This is kqp. These cancel, okay, which implies the following, that k0k is equal to pi 0. Okay? But our factorization tells us what that we can factor this thing so that pi 0 is a geometric cover, or an arithmetic cover followed by a geometric cover. So we have g0 followed by the arithmetic cover, which was delta 0. Okay, and this thing is really kk0, or k0k, delta 0. Okay, so so now we have that. So then we have that k0k is equal to. So we have this part here, and we're plugging this part in. K0k, delta 0. These cancel, which implies that delta 0 is 1. Okay, so this shows that the cover is completely, hence the cover is completely arithmetic. Okay, which means, you know, I mean, let's say slash a base change cover. Okay, and this can be summarized in a number of ways. Remember that, so that this means that delta of x is completely contained in pi of x0, or you can say that pi of x0 is the inverse image of a g0. Okay, so these are kind of two different ways of doing it. Okay, so yeah, and that completes the proof. Okay, so this shows that this condition here is gives all the base change ones, and then once we have all the base change ones, we intersect over all of them, and that concludes the proof. So we conclude the recovery of delta of x by intersecting over all of these. And then without loss of generality, we can assume that they're Galois, which will give us the clopedness. Okay, so yeah, and that's where we were going. Let me come back to the finally. Let's see. It's really a long bit. Maybe I didn't need to say so much, but yeah. So that's how to do it. So yeah, this is this characterization now. Okay. Thanks for watching.